Hey everybody. So I want to frame this video around this particular research paper, which is Physics of Language Models, Part 3.3, Knowledge Capacity Scaling Laws, which is put out by Meta and is put out in April of this year. So this is a rather earlier this year paper, but this paper outlines the full physics behind LLM models very specifically. And so a lot of people, they ask, are LLM models, do they produce deterministic outputs as opposed to probabilistic outputs? What's the knowledge capacity of an LLM model? Do they actually learn? Where do they store that knowledge? How do they store that knowledge? Etc. And so this paper from Meta breaks down all of the physics involved and strips away a lot of the demystifies a lot behind the LLM model knowledge. And then so I use this knowledge myself a lot in kind of my research and in my training practices, etc. And then I've noticed that Meta tends to be very far ahead, oftentimes with regards towards architecture and model training. And I think it's, things like this that kind of back up and support that as to why. And so distilling down the knowledge from this research paper, I kind of distill it down into the 4 laws of LLM knowledge. And these will grow, right? These are just the 4 laws that currently exist right now. But these are like hard and fast and true when it comes to LLM knowledge and what we know about LLMs at the moment and with regards towards the physics of LLMs. And so first is that you want to expose the model to the data set at least 1,000 times. This is necessary to reach the optimal knowledge storage capacity of 2 bits per parameter. Without enough exposures, for example, only 100 exposures, the capacity is halved. And so there's a lot to unpack within this particular statement. The first one there is that so there is a limit as to the knowledge per parameter in an LLM model, which is 2 bits per parameter, right? So every LLM model, no matter what, no matter the size of it, per parameter, it can store 2 bits of information. But in order to get that 2 bits of information into the parameter, into it stored permanently, you need to expose it 1,000 times. And then so that can scale up. And then so what that means is if you scale that up very simplistically, a 7 billion parameter model has more parameter capacity than say Wikipedia and the Library of Congress combined, which would be like all of pretty much the biggest text documents that you could find combined, right? And then so that's what the 7 billion parameter model. And then so that gives you an idea, right? Like when people say that the scaling limits are due to data, you can see that in a lot of why there's been an explosion of kind of synthetic data and everything around that. I just highlighted the 2 biggest examples, the 2 biggest data sets in the world are covered by a 7 billion parameter model, and we already get up to 400 billion plus. We already want to go to 1 trillion, and then so you're talking magnitudes, hundreds of magnitudes more data that is necessary in order to fill that amount of parameters. You can scale up those parameters, but it doesn't mean anything because we need to scale. We need 1,000 times. We need 2 bits of data and to expose it 1,000 times per parameter. If it's a 1 trillion parameter model, that's a lot of data. It's 2 bits times 2 times a trillion, and then so 2 trillion bits, and then quite a bit of data. And then so second thing is, and this is important, do not quantize past int 8. And then so quantization to int 8 maintains the model's knowledge storage capacity, but if you go further, like int 4, it significantly reduces the capacity to about 0.7 bits per parameter. And then so it's very significant, and it's a very sharp drop, right? It's a curve like this, and then just a line just straight down, meaning that you go down to int 8 and you're totally fine. And then so quantize 8-bit quantization. But then the second that you go to that 4-bit quantization, you automatically go. So quant 8, you'll be at 2 bits. You can have 2 bits per parameter. When you get down to quant 4, all of a sudden it drops to 0.7 bits per parameter. Like just that shift from 0.8 to 0.4, right? And then it will always be that major shift beyond that. So when you talk about like the 1.58 bit quantization, it's still this same logic and this same scaling rules behind it. So that is kind of interesting, right? To note that as far as the math is involved, that 1.58 bit quantization is the same as int4 quantization. It's going to be 0.7 bits per parameter that you're going to be able to store. So in theory, like in practice, like you don't want to go below int8. If you ever do go below int8, why not go to quant 1.58? Because that seems like the way to go, right? In this instance. So just highlighting those things there. And then this third one is extremely important as well, right? And then this is this is the biggest gap that still exists, and the biggest like hurdle, like the biggest like prize to be won within AI research is around this. So elimination of junk data. And then junk data dramatically reduces the model's ability to store useful knowledge. The more junk, the more it hampers the model's capacity to retain valuable data. To mitigate this, appending domain-specific tokens like wikipedia.org to useful data helps. So a few things to unpack here. The very first thing is that good data versus junk data matters, right? Garbage in, garbage out. And then the second thing is that like giving the model hierarchies of data, like a hierarchy of data is very important, and that's what this notes within it, right? And then a hierarchy of data meaning a hierarchy of data sources. And then so this is a scientific data source would be higher on the hierarchy than this is from like TMZ. Right, and then that kind of thing, and then like specifically rating out and knowledging out and creating a graph and a network that houses and maintains those things, and then giving that to the model. But then secondarily, most importantly, not giving that model the TMZ data up front, giving it just the straight scientific like papers, right? And then but within that, that raises the question of what is junk data versus good data. And then this is like, that's where the whole argument and question and all of like the gotcha comes in within this, right? Because that's not a universal answer. There could be instances where you do want to train a model on TMZ data, and where TMZ data becomes the optimal solution for the model. And so if you rule that out and then you create a rule where it's the exact opposite of that, where you do, when you do run into that situation or you do face that, it's not a universal situation after all, right? Because you've ruled that out. And then so just keeping that in mind, within that, it seems like a simple problem up front, right? Okay, just eliminate the junk data. Easy, right? But what is junk data? And then that's what the big question comes down to. And then rule number 4 is like law number 1, right? Like it's like don't talk about Fight Club and like ever, which is that the cap is always 2 bits per parameter. Like as far as we know, that mathematics is concerned, the people, there's a person that has won a Nobel Prize around this. You're not going to get more than 2 bits per parameter. This is the maximum achievable knowledge storage capacity when the model is trained optimally, ensuring that each parameter can store 2 bits of factual knowledge. And then so again, that 2 bits is hard to get at and then hard to maintain. And then the last, it would almost be a 5th law, but it's not quite universal enough to be the 5th law on here, is that it's important to note within this meta paper, the newer model architectures, like the newer Llama models and the GPT architectures are in this paper, as this paper shows, they get beat by the BERT architecture and the GPT-2 architecture. Like the more simple architectures can actually store more factual information within this. So they're easier to train at the end of the day than all of these like model of experts and all the gating that we put in, and the softmax, everything on top of it. Like it's essentially what this paper is showing is that like the more complexity that you're adding on top of it, the harder it is to train the model, which makes sense, right? And then so that's when it comes in. And then where that impacts the model is within this equation right here, meaning that if you are putting on all of these extra things, your particular model isn't going to be able to store 2 bits per parameter. Your particular model might have a cap of 1.5 bits per parameter. 2 bits per parameter is just the hard cap, right? So that's the important thing to note within this, is that 2 bits is the hard cap and can definitely be decreased below this. If you quantize to int 4, you automatically decrease, your cap is now 0.7. No matter if you go through and then you put in like softmax and then gating parameters and other things like that, perhaps all of a sudden your max is 1.5 and then that's it, and you're not going past that, right? And then so it's, again, 2 is like the theoretical max, like it's light speed, right? We're not going past light speed. And then so 2 bits per parameter is light speed in this equation. And then so these are the laws of LLM knowledge as broken down and as demonstrated by Meta and as demonstrated within neural frameworks as well. That's kind of where all of this comes from and starts from. But just highlighting this paper and highlighting these concepts overall, because a lot of people ask about these questions, right? How exactly are the models working? Hopefully this gives you a better understanding overall, kind of mathematically what's going on within these models. If you like this type of content, please like and subscribe. Thank you very much.